For thousands of years, mankind looked at the sky and wondered, what's out there? Where did it all come from? By studying the night sky, astronomers found that the universe expanded out of a single point in what we call the Big Bang. Here on Earth, physicists create little bangs by smashing atoms together, recreating the conditions very similar to what the universe was like 1 microsecond after the Big Bang. Interesting acoustic signals left over from the Big Bang have been detected in the cosmic microwave background radiation. The temperature fluctuations present in this cosmic mag come from quantum fluctuations from the very early universe, which were then stretched out to cosmic sizes by inflation and propagated as density or sound waves in the early universe. To unveil the sound of the little bangs, let's look at what goes on inside an atom smasher first. At the Relativistic Heavy Ion Collider at Brookhaven National Lab on Long Island, New York, gold atoms are being stripped of their electrons, and then the remaining nucleus are being accelerated to nearly the speed of light. At these speeds, relativity flattens the gold nuclei. These are then smashed into each other. What is produced is an extremely hot and extremely dense fireball of quarks and gluons called the quark-gluon plasma. This fireball is as hot and is as dense as the universe was at 1/1,000,000th of a second after the Big Bang. As the hot fireball expands and cools, the quarks and gluons form composite particles, which then leave tracks as they stream through the detectors. This is an image of the aftermath of one of those collisions. Since the gold nuclei are lumpy, each collision is unique, and no collision is homogeneous. These density lumps at the start of the collision can show up as hotspots at the end. So, just like quantum fluctuations in the early universe show up in the cosmic microwave background, we expect to see fluctuations from the beginning of the little bangs in the tracks in the detectors. Mapping the cosmic microwave background requires precise temperature measurements at more than 2 million spots in the sky. Unfortunately, each gold collision produces at most several thousand particles, making it impossible to create a similar map. But whereas there is only one universe, billions of collisions are created in the laboratory. And from these, we use correlations to accumulate information and then look for evidence of hotspots. And this data shows that fast particles come out from the collisions close to each other. This is exactly what we would expect if density fluctuations survive throughout the expansion and then are projected into the detectors. We use this data to extract the frequencies and their strength at the end of the collision. But to know how that sound developed, we determine how the acoustic horizon expanded with time. Just like the horizon defines how far we can see, the acoustic horizon defines what sounds we can hear. Initially, only the shortest of wavelengths can fit inside the horizon, so we hear the highest tones first. Then, as time passes by, longer wavelengths and lower tones become audible. Finally, as the system becomes too cool and too spread out to interact anymore, we hear the final note, before the silence of the vacuum. The frequencies you'll hear have been scaled to be audible to the human ear. So here is the full acoustic picture of the collisions. Here is the sound of the little bangs.